So molecules with a stereocenter are not automatically chiral. It's a true statement. Like, here's two examples. These molecules that have internal, so these are internal planes of symmetry, right? So they look exactly the same on each side. These are called meso compounds. Right, so these are meso compounds. All right, down here, we're looking at solutions that are composed of only one of the two enantiomers. These are considered to be either optically pure, you could call it optically pure, or you could call it enantiomerically, because it's an enantiomer, enantiomerically pure. Boom. Solutions that are composed of 50% of each of these are not optically active, right? The reason being that 50% of them rotate the light one way, the other 50% rotate it the other way, and those cancel out, right? 50% clockwise, 50% counterclockwise, both cancel out. And these are called racemic solutions, or racemates, racemate. When we're trying to identify these as being one of these relationships, right, we want to look at the stereocenters and figure out what's the relationship. Okay, so I look here first at the bottom one, because I see this has exactly the same arrangement, right? H on the left and H2 on the right, CH2, CH3 on the bottom. Boom. So this is exactly the same. The top one has the H and the OH are switched, and the CH3 is in the same place. Okay. If you were to move all three groups, we could take a second and try to figure out, is this the same representation and a different configuration, right? Because if you rotate all three groups clockwise, like if I moved, you know, if the CH3 came down, the H came over, and the OH came up, that would be exactly the same, right? But I see that's not what happened, right? The CH3 is in the same place, and only the OH and H switched. This must be the opposite configuration. So with two stereocenters, right, there's two stereocenters, 1, 2. One of them being the same, one of them being different. These are diastereomers. Next up, go look at these guys. This one's actually pretty straightforward, right, when something's identical. And in this problem, we haven't rotated anything. CH3 is in the same spot, H in the same spot, OH in the same spot, H2, H2, everything's in the same place. This must be identical. No big deal. And down here, let's take a look again. So H and H2. Wait a second. This is a really easy one if you draw that mirror in the middle and you just check. Oh, CH3 is in the same spot because it's in the middle. OH is reflected across, right? The closest group on this side is the closest group on this side. The furthest group on this side is the furthest group on this side. Same thing for NH2, right? It's the closest to the mirror, closest to the mirror, furthest from the mirror, furthest from the mirror. Boom. This is a mirror reflection. Both stereocenters, both chiral carbons have flipped, so these are enantiomers. All right, to figure out which molecules could have enantiomers, you have to flip them, right? We're going to do a mirror flip, and then you kind of have to challenge yourself a little bit and think about, whether or not you can superimpose what we're drawing back onto the original, right? So this one, if I mirror flip it, well, look at that. I have this. And that's still on a wedge because wedges and dashes won't flip. And this is also on a wedge, OH. Oh, that's exactly the same molecule. That's not an enantiomer. It's literally the same. I'm going to do the same thing here. So this one will actually have a little difference in that I'm going to have this OH on the dash closer, and this OH on the wedge will be further. It looks a little bit different. But I can actually just flip this upside down, or if I do it's called a pancake flip, this will look exactly the same. Down here, all right, once again, I'm going to do move this over a teeny bit. There we go. I'm going to do a little wedge over here. OH, and we'll do a wedge up here. OH, okay. So now, Just kind of looks different, doesn't it? What if I rotate this? What if I take this molecule and I rotate it? Or if I rotate it 90 degrees? Well, actually, let's literally rotate it using, the powers of graphics manipulation, right? Control X, Control V. Oops. Control V. Hey, go on now. Control X, Control V. There you go. And so I'm going to rotate this 90 degrees. Boop. Right. Oh, well, would you look at that? That's actually still, OH on a wedge, OH on a wedge, exactly the same conformation. That's the same molecule. Okay. So we know the answer has to be D, but, let's take a look and just confirm what's going on there. So if I draw a mirror, I do a situation like this. I've got the wedge up top. I've got the dash on the bottom. Okay. So this looks similar. It's different. You might be thinking maybe we can just rotate it again, right? Well, let me go ahead and show you that we cannot. So if I rotate it 90 degrees, oh hey, look. Now I've got the dash up top and the wedge on the right. So that's not the same. That seems pretty good. Well, what if I pancake flipped it? Well, if I pancake flip it, what's going to happen is that this ends up on the other side, right? So pancake flip is going to be like a up and over situation. So I'd still have my diamond shape. But now if I pancake flip, wedges become dashes. Dashes become wedges. Oh, that's not the same, right? And I can't rotate this either to get those in the same spot, right? And we could keep trying to play around with it, but we kind of already know that there's no way to get it to be the same because it's an enantiomer. So this question looks a little more intense than it is. It's actually not that bad if you break it down. The first thing to check out is whether or not the core molecules are the same, because if they're not, you would have a constitutional, right? So a constitutional versus conformational, right? So these are all conformational isomers. And so they're the same, so it's some sort of conformational isomer. So we just need to look at the 2s, 3r, 2r, 3s, okay? I see that the first, right, carbon 2 is flipped, right, s to r, and carbon 3 is flipped. They're both flipped. They're both the opposite, right? Diastereomers keep at least one the same. So we keep at least one the same. Meso compounds need to have an internal plane of symmetry, which I cannot imagine this is going to work out to be. We could try and figure that out, certainly. And they're not identical compounds, right? We know that that's just not the case because they're conformational isomers with the different configurations. So I'm going to feel pretty good that these are actually enantiomers of each other, right? So these are actually enantiomers. Let's just sneak that over there, right? So if they're enantiomers, we're in. That's the end of the day. But we can also draw them out just to check, right? So if I was to do a quick drawing, I'm going to pause it here and take the time to draw this out for you. Once these are drawn out, we can see that there is not an internal plane of symmetry, right? Sometimes you might have an internal, what's called, like, I like to think of it as like a shark fin, from left to right, a shark fin kind of slices through the molecule. But there would not be an internal plane of symmetry here because the bromine is leaning towards us and the oxygen leans away from us, right, on both these sides. We would really need to have just a different molecule to have that kind of symmetry. So yeah, we can feel really good that these are definitely enantiomers since both of the stereocenters have flipped, and that's going to create a mirror image.